In construction, concrete is almost never used without steel reinforcement. This is due to the cracking of concrete and its inability to transfer tension loads. But what's the purpose of the transverse reinforcements, also known as stirrups? In this video, we go deeper into the load-carrying mechanics and the actual reason why stirrups are needed in concrete beams. The main purpose of a beam is to transfer loads to the supports to enable open spaces. Beams are some of the most common structural members that appear everywhere. In this video, we'll limit our focus only to concrete beams under gravity loads, though a lot of the concepts are generic and applicable to all types of beams. Since beams are generally always subjected to bending, as explained in one of our older videos, bending a member causes stretching of the material on one side and crushing on the other side. The amount of stretching and crushing that the material feels is dependent on the length, size, and material of the beam, but of course the magnitude of the load as well. The length is the most significant parameter, which makes longer beams more susceptible to bending. As the beam continues to be bent, cracks start to appear at the bottom side, which is being stretched. Once a crack develops, the concrete loses its ability to carry tension loads, and therefore the tension has to be taken by the steel reinforcement. Besides stretching and compressing, the material also feels shearing forces. These forces attempt to shear off the beam, as shown here. For simple beams, shearing forces are the highest near the supports due to the high forces exerted from the support, while zero at the midspan of the beam. These forces are very destructive and usually cause sudden and brittle failure of the beam. The bending and shear loads are the most important design considerations for a simple beam loaded concentrically. These forces guide the design of the beam in terms of size, amount of steel, and length. But how does a concrete beam resist these forces, and why is the steel reinforcement even necessary? The answer lies in the nature of concrete as a material. Concrete is strong in resisting compression forces, which makes it ideal for columns or walls. However, concrete is incredibly weak in resisting tension forces. In fact, in design, engineers generally assume tension strength to be zero. This is because in structural analysis and design, concrete is assumed to be cracked, which prevents transferring of tensile forces. In reality, even cracked concrete has some small tension resistance. However, using this strength is risky and unreliable. For that reason, engineers are forced to reinforce the section of the member that is expected to experience tension. For simple beams, as we saw earlier, this is always the bottom side. But for some more complex arrangements, steel reinforcement could be required on both sides of the beam, if tension forces are to be expected. One such example is a cantilever beam that has the top material in tension or stretching and therefore has the top part of the beam reinforced. But if longitudinal rebar takes tension on the bottom and concrete takes compression on the top, then what is the purpose of the stirrups? Many people in construction believe that the stirrups are only there to hold the longitudinal reinforcement in place. Though that is true, it is not the main reason for their use. Similar to the longitudinal reinforcement, the stirrups are also there to resist stresses which the concrete alone is not great at resisting. These stresses originate from the shear forces mentioned earlier. In fact, stirrups are also often referred to as shear reinforcement due to their purpose in resisting shear forces. Stirrups get engaged when an inclined crack occurs in the beam. These cracks are often referred to as shear cracks, however, they are actually caused by tension forces, as we will see later. The cracks are microscopic and most of the time are invisible to the naked eye. However, their presence is crucial in the design of concrete structures. Once the concrete is cracked, no tensile forces are transmitted across the crack. The only force that keeps the two sides of the crack from sliding past one another is the interlocking of the concrete aggregates. The interlocking force can be very strong and can provide between 33 to 50% of the shear resistance of a beam. However, as the crack widens, the interlocking is significantly weakened and the resistance drops which allows the two sides of the crack to slide past one another. The sliding in granular materials causes motion perpendicular to the direction of the applied force. This is the critical point where the stirrups get activated and prevent full separation and sliding of the concrete. The stirrups prevent the sliding motion and begin to carry the shear force that used to be carried by interlocking. Interlocking tends to lose its resistance due to the widening of the crack, and therefore it is unreliable and is ignored in the calculation of the shear capacity of the beam. In fact, the only concrete shear resistance for regular cast-in-place beams comes from the uncracked concrete on the compression side. The intrinsic concrete shear stress is often insufficient for a safe design. Based on the applied shear forces and the width of the inclined crack, engineers can calculate the amount of reinforcement needed. For higher shear loads near the supports, the stirrups are placed closely, which ensures that several of them will be engaged within an inclined crack. Near the middle of the beam, where the shear forces are low, designers tend to reduce the spacing or completely eliminate the stirrups. Earlier we saw that the shearing forces act perpendicular to the beam, and yet the crack tends to follow a curved trajectory. Why is this the case? Why doesn't a beam crack vertically down across its entire depth? To answer this question, we need to get slightly more technical and dive into complex stress states caused by combined loading. When a beam is bent, its cross-section is subjected to normal and shear stresses. The distribution of each varies along the cross-section as shown here. To be able to predict the propagation of the crack, we need to be able to determine in which direction the beam is experiencing the highest tension loads, since it is always the tension load that actually crack the concrete. The direction in which the highest tension loads act is called the principal direction. This is the direction in which the material does not experience any shear stresses, but instead all of the energy is stored in the normal stresses. This direction is different along the depth of the beam and is shown here. We won't go deeper into how to calculate this direction. If you're interested, we suggest looking up topics such as stress transformation and Mohr circle. Since this is where the highest tension stresses act, the crack tends to propagate in this direction. At the bottom of the beam, there are no shear stresses, and therefore the principal direction, also known as direction of highest normal stresses, is already aligned along the length of the beam, which explains why the cracks start out vertical at the bottom of the beam. However, as the crack propagates towards the inner part of the beam, the shear stresses experienced by the material are non-zero, which means that this is no longer the direction with the highest normal stresses. The principal direction is now slightly inclined, and therefore the crack tends to also propagate along the inclined path. It's because of these stress states that cracks follow a curved trajectory occurring near the ends of a simple beam. Consequently, that's why the shear reinforcement is placed in those regions. We hope this gave you a good introduction into the concept and application of shear reinforcing. Thanks for watching another video of the Engineering Hub. We love a good discussion in the comments, so let us know what you think about this topic or share some ideas or experiences that you have encountered. If you liked and enjoyed the video, consider also subscribing to our channel. This is the easiest and most effortless way to help our channel and motivate us to produce more videos. Thank you and see you next time.